Hello, and welcome to Functions and Function Notation. This will be an intermediate algebra look at what it means to be a function. So we're going to start with two definitions, and the first definition is that of a relation. A relation is just a set of ordered pairs. It's just things that go together, like peanut butter and jelly. We're going to talk mathematically for the most part. A function is a relation, all right, so there's some sort of ordering together, in which each input is related to only one output. For each input value in the domain, you must have one and only one output value in the range. So for me, I think of this as the input is people, and the output are places. So can you be in two different places at the same time? Right? Could you be studying in the library for your midterm while you are at the bar doing trivia contests trying to win a free thing of fries? No, probably not. If you can, then your library really needs to kind of step up a little bit. Or you've got a great library. It depends on how you look at it. Several people could be at the library studying together, so a bunch of different inputs can be all together at the same location, but you cannot be in two places at once, and that's really what it means to be a function. So let's determine if these given sets, first of all, are functions. Determine whether the following descriptions of relations are functions or not. The set A, which is the point 2, 5, 4, 8, 10, 8, and 20, 15. If we look at the inputs, 2, 4, 10, and 20, I ask myself, does 2 go anywhere other than to 5? No. Does 4 go anywhere other than 8? No. 10 also goes to 8, but maybe their buddy's studying at the library. That's all right. So this is a function because everything seems cool. All right, now the set B. The set B, 1 goes to 3, 4 goes to 7, 3 goes to 1, and 4 goes to 9. Wait a minute, I thought 4 went to 7. That you're like, hey, I'm gonna go stay with my friend over here, but you're really at the party at your boyfriend's house or your girlfriend, whatever, we don't judge, whichever way. 4 can't go to 7 and 4 can't go to 9 at the same time, so this is not a function. All right, the 4 messes it up for everybody. Up here, the 8 didn't mess it up. 2 people can be in the same place, that's cool. But you cannot be in 2 different places at the same time. All right, example number 3, given this data set, days of the week, and temperature. Notice Monday is 90, Wednesday is 88, Saturday is 91, Monday is 93. Like usual, Monday ruins it. So this is not a function. All right. The population of New Mexico each year. Wow, we really have to kind of slow down and think about it. The population is our output. Each year will be our input. Now each day we might have a different population, but overall at the end of a year, I believe we can only have one population listed. I'm going to call this a function in that the Census Bureau would determine it as a function, not thinking of it as different parts of the year, but directly as it states, the population of New Mexico each year. All right. Now, to determine if things are functions, we could use a vertical line test. And the vertical line test for a function states, if any vertical line intersects a graph in at most one point, the graph represents a function. So if any vertical line hits it more, then it's not a function. So this is a horrible example. I can see right here, this is a vertical line that hits it a couple times. Here's a vertical line that hits the graph 3 times. This one is not a function. This is why I give my students copies of the blank notes as well. Because then I write over them and sometimes you can't see dots. Take any vertical line. Let's see if I can draw a vertical line. any vertical line that I put, choose any x value. Anywhere it hits the graph, it hits in at most 1 point. So this is a function. Here's a vertical line, the y-axis. The y-axis hits the graph in 2 places. Here's a line that hits it in 2 places. Here's a line that supposedly only hits it in 1 place, and here's a line that doesn't hit the graph at all. Now these 2 lines are fine. If the vertical line doesn't hit the graph, no big deal. Vertical line hits the graph once, no big deal. But if a vertical line hits that same graph, any vertical line hits it more than once, it is not a function. And then finally, we have this nice constant function. It's a horizontal line. Any vertical line that I put in is only going to hit this once. So this is a function. Normally, I would use like a ruler or something, but you can't see the ruler I put against my screen, so I know better, and I just drew some random lines. I do not suggest you draw lines on your computer screen unless, you know, you got the fancy tools too. They're not all that fancy these days. All right, so in general, mathematicians have shortened ways of doing many things. One of these shortcuts is in how we write functions. Rather than saying the mouthful, y is a function of x, we would write y is a function of x. So y is a function of x are these 4 lines. So we could use function notation for all of our model problems. So let's look at some examples. Specify the input and output variables and their definitions and units. Determine whether or not each relation is a function. Okay, so inside the parentheses is a, so that's our input. A, and it tells us in the problem, a years old. A years of age. Now our output is labeled by G, and what is it equal to? It's the grade level. So G is grade level at A years. Now, is this a function? No, it is not. I happen to be in, my birthday's in April. So in March, I was one age in a certain grade, and at the end of by the end of April, I was another age, and as in the same grade. So a 7-year-old could be in 2nd grade, could be in 1st grade, could be in 3rd grade. They might even be like a Doogie Howser type of person. I'm going to say this is not a function. So many things can happen. Salary A in dollars of someone who is A years old. Age in years, this is our input. Our output in blue is S, which is salary in dollars. Okay, so do all 48-year-olds make the same amount of money? Nope. All 30-year-olds? Nope. This is not a function. So do we have any real-world descriptions that are functions? Let's see. Postage, P of W equals postage in dollars. It takes to mail a first-class package weighing W ounces. W is ounces. It's a weight. It's our input. Our output is how we name the function. That's P, that's postage in dollars. And in the United States, this is a function. It's purely based on weight as you mail your ballots in October, so you can mail in your ballots. Vote, people. Vote, Americans. In other countries, too. It's, you know, if you're given the opportunity to vote, you should. Domain of a function. The set of all real numbers that make the function defined is the domain of a function. Avoid division by zeros and negatives under square root, and your domain's pretty good. All right, so we only have to look at division and square roots right now when it comes to domains. The range is the set of all possible output values resulting from all the values of the domain. Wow, I read that wrong. The set of all possible output values resulting from all the values of the domain is the range of the function. A graph is very helpful in determining the range of a given function for now. As your algebra skills get better, we'll have other techniques, but for intermediate algebra, I highly recommend the graphing calculator for determining your range. All right, so let's look at some functions. And to start out, I'm going to make each of these a different color. I'm going to change up my colors here. Let's use a forest green. There we go. All right, so my f of x is going to be in black. And instead of calling it f of x, I'm going to write what I call the skeletal form. And it takes wow, I'm not speaking well today. Takes the x and opens it up and calls it a something. I'm going to leave it blank. Wherever that x was, I'm going to leave it blank. My g will be in green. I don't want the x. I'm doing this for a reason. G is negative 1.25 times something plus 14. And in blue, I'll have my h of x, which is 2 times something squared minus 10. Now, in the original statements and the type values, they were x's. As I wrote them out underneath in the pen, I called them something, but I left them in open parenthesis. So if I want f of 3, I know that f has the structure of 7 times something plus 2. And this tells me exactly what my something is. Let's find red again. The something is 3. So everywhere I saw an x, now I'm going to put a 3. And I simplify. 7 times 3 is 21. 21 plus 2 is 23. So my answer is 23. In h, right, our blue function, h, is h of something. Look at me doing this x value in here. H of something is 2 times something squared minus 10. Well, what is that something? That is a negative 4. And then I just simplify. Order of operations tells me what's in parentheses is being squared. So negative 4 times negative 4 is 16. I almost called that negative 8. It's 16. Negative 4 multiplied by negative 4 is 16. Don't forget that minus 10. That's why we write the form down. The skeleton, the structure of it, and then we put in the guts of what we're trying to evaluate. H of negative 4 is 22. And we are finished. I need my green pen back. So let me grab it there. All x such that g of x is 15. So what this is telling me is this whole g of x, this entire g of x is being replaced by 15. So if I had g of x equals negative 1.25x plus 14, actually let me do this a different way. Let's do it exactly as it says. Find g of x. It's right there. Negative 1.25x plus 14 has to be equal to 15. Right? Just substitute in the entire expression using the x. So we're not putting the 15 in for x. Right? That would be an input. That would be an evaluated at. This is the output. To solve, we'll subtract 14 from both sides. Don't forget that x. That x is super important. Now to get x by itself, a huge negative sign for some reason. This is one of those times where I wish I was using fractions. It would be much easier. But if I have 1 and I divide by a negative 1.25, I will get a negative 0.8. All right, so x value of negative 0.8 will give me a g of x value of 15. All right, the domain and range of each function. My function, f. The domain will be all real numbers. Remember, the domain only cares about dividing by 0 and negatives under square roots. F doesn't have any denominators, and it doesn't have any square roots, so the domain's all real numbers. Now, we know that F is linear, and we know that a linear function is a straight line graph, and this one continues forever in both directions. They all continue forever in both directions. So the domain and range happen to be all real numbers. Our function g is also linear. Anytime you have a linear function, that's going to tell you something about the range. The domain, no denominators that have variables, no radicals. So the domain is all real numbers for a linear function. The range is also all real numbers. When we're looking at h, though, h is not the same as the others. This happens to be a quadratic. And my students haven't talked about quadratics yet. Those will come later. You could skip ahead and check out some of the videos if you're not one of my students, because hopefully I'll have them all up by then. A quadratic, there's no denominators, no radicals, so the domain is all real numbers. But let's take a quick look at the graph. So I'm going to go to y equals, and I'm going to clear out what we have here. That was from a different video. I just forget to clear my history with each new video. 2x squared minus 10. And since I have no idea what my window is right now, I'm going to put it on a Z standard window. And it looks like I could see everything, but I'm going to go a little bit lower on my y values just to make sure. Well, look at that. Everything comes down and it stops here at negative 10, and then it goes back up. So my range says that negative 10 is the lowest I go, but it goes forever up. So negative 10 has a square bracket because we can include negative 10. That's the lowest we could go. And you go up on to infinity. Now, if you didn't want to do this graphically, if we look at 2x squared minus 10, now x squared will always be 0 or larger. 0, oh, that's horrible notation. X squared will always be 0 or larger. 0 times 2, a positive 2, will always be 0 or larger. When I subtract 10, negative 10 or larger. And that's exactly what we found here in the range. All right. That is it for this video, functions and function notation. Highly recommend the skeletal form so that you could just fill in those values, that the guts, the meaty part of the function in order to solve. Thanks for listening.